Okay, there's some more stuff for you guys. This is part two. There might be a part three actually, because I really want to make this go a little piece at a time. I want to talk about friction, and friction's pretty easy. Okay, first of all, what is friction? Well, if I have two surfaces rubbing against each other, let's say I'm doing this, right? I'm doing that. I'm warming my hands. You do that. What do you feel? You're going to feel heat, when you're cold, maybe you're out hunting or something. You're like, oh man, my hands are cold. So you rub them together and you feel there's some resistance to that motion. If you're sanding, you take up sandpaper on a block and you're sanding some wood. Well, what's happening? It takes some effort to do that because of friction. In that case, when I have sandpaper on a block and I'm sanding some wood, there is a high coefficient of friction there because there's a lot of friction. But if I have an ice cube, say I have an ice cube and I have a Teflon pan, a non-stick pan, and I take that ice cube and I'm pushing it around the Teflon pan, it's pretty easy to do that. So there's a low coefficient of friction. That coefficient of friction is given by that symbol. And it could be for static friction or it could be for kinetic friction. Now, static friction, the coefficient of static friction is usually greater than the coefficient of kinetic friction because static friction is how much it takes to just start movement. Kinetic friction is the friction as the things are moving between surfaces. So in general, that's not always the case, but 99% of the time you're going to see that. Static friction and kinetic friction, and these are the coefficients. All those coefficients do is tell you, hey, how strong is that friction between the two surfaces, or how uh, how high is the magnitude, and it helps us to wrap our minds around this frictional force. So the frictional force is usually like, again, my notation might be different in the book. I'm really old school. We learn to use script letters or Greek letters for things. So I'm used to that. So little f we used for friction. So we have static friction force is equal to the coefficient of static friction, and that's a number that you could either be given or you could solve for, times the normal force. And that normal force is mg. Now, if you're on an angle, it'll be mg cosine theta. But I'm going to stick with just flat surfaces for you guys. Likewise for kinetic friction. Mu sub k times n. So let's think about things. Let's think about, let's say you're sliding on the ground. There's a problem. Well, look at a problem here about some guy sliding into first base or home base or something. If I'm just moving along and let's say I have a certain velocity, okay, I'm not accelerating on my own. I'm just have a constant, well, I have a velocity. And eventually I'm going to slow down because of friction. So you know this. Let's say you have a hockey puck and you slide it across the ice. It goes pretty far, but it does eventually stop because of friction. On Earth, we don't have perfect non-frictional surfaces. So let's say I'm sliding. The only force that's acting on me is the force of kinetic friction. And if there is a force acting on me, then we're going to have Newton's second law come into play. Mass times acceleration is equal to that force. So that's one thing I think that's hard for people to wrap their mind around. Again, if I just set something in motion, once it's in motion, there's only one force acting on that, and that is the force of friction. So let's take a look at a problem. It's actually problem number 1 on page 169. And it talks about a baseball player that's sliding into third base, according to this problem, and he has an initial speed of 7.9 meters per second. Okay, so he's just sliding along. So you know that eventually, because of his body sliding on the ground, he's going to stop because of friction. So what we can say is the only force acting on him is kinetic friction. So force for kinetic friction, that's going to be equal to his mass times acceleration. And this question is saying, hey, how far does he go before he stops? Well, if you remember this old equation, this is one I'd have in my toolbox. This is one we learned a long time ago. The final velocity squared equals the initial velocity squared plus 2a times delta x. And if he's going to stop, well, the final velocity, that's going to be 0. And we've seen that many times. So let's go back to this idea. You might look at a problem like this and you might say, I don't have enough information to solve this because I don't have the mass of this person. Well, let's see if you need the mass of this person. The kinetic force of friction is equal to mu sub k times the normal force. What is the normal force? It's m times g. And that's equal to mass times acceleration. So what can we say here? Mass can cancel. So in this case, if we know the coefficient of friction and we know g, which we do, we can solve for the acceleration. So the problem tells us, it says the coefficient between the ball player and the ground is 0.41. Remember, there's no units on that. It's just a coefficient. So 0.41 times g, that's going to equal the acceleration. Now, the acceleration, you have to understand, is opposite to the direction of motion. So your value of acceleration is actually going to be a negative number. So let's go ahead and solve this problem. Okay, well, 0.41 times g. G's approximately 10. So let's get a real number here. 0.41 times 9.81, that's equal to 4.02. That's equal to acceleration. But it's actually, you have to do a little intuition here. It's going to be negative because it's acting in opposition to his motion. So lo and behold, if we go ahead and use our equation, v final squared equals v initial squared plus 2a delta x, and we know the initial velocity, his initial velocity is 7.9 meters per second. So let's go ahead and work on this equation. Let me adjust my camera a little bit. Again, I'm working with a pretty basic setup here. So this is going to be 0. So 0 is equal to 7.9. I'm going to leave the units off just so it doesn't look cumbersome. Now, acceleration is going to be negative, minus 2 times 4.02 times delta x. Oh, this has to be squared. I apologize. All right, so 7.9 squared, let's get a number there. So that's going to be 0 is equal to 62.4 minus, okay, this is going to be 8.04 times delta x, where that's going to be the stopping distance. I'm going to bring that number over to the other side. So let's go and say, okay, so negative 62.4 is equal to negative 8.04 times delta x. And then I can divide both sides by negative 8.04. So my delta x, the distance in which he travels before he stops, right, so that's going to be divided by, so he's going to go about 7.7 meters. So sometimes, and this is something that when you first start learning physics seems confusing, you think you need a piece of information and they don't give it to you. Well, if they don't give it to you, something in the problem tells you that you're not going to need it. So I'm going to do a problem like that on the quiz or the test, whatever you want to call it. It might be like, I might say, Mackenzie's sliding her cell phone over to Killian on the lab table. And I give you the coefficient, and I tell you the initial velocity, and you're going to say, how far can you slide the phone? or whatever. I think you can figure that out. Let's do another one. All right. Oh, let's take a look at question number 3. I'm going to save some paper here. And number 3, I know you probably don't have a book here, but I'll show it to you really quick. Hey, I'm willing to spend hours making these videos if it'll help you. If I can get this thing in focus here. Maybe I'll just read it to you. This is not, I got to get it better set up, guys. So maybe Santa will bring me one. Hopping into your Porsche, you floor it and accelerate at 12 meters per second squared without spinning the tires. Determine the minimum coefficient of static friction between the tires and the road needed to make this possible. So let's think about this. If you are starting from rest, you have to put in static friction to get you going. So you're starting from rest, you got to go. You have to overcome static friction in order for this to happen. So the only force initially is the force of static friction. And that's going to equal mass times acceleration of your car. In this case, you're told the car accelerates. We are given the acceleration in this case. It is 12 meters per second squared. And eventually, we are trying to find the coefficient of static friction. So remember, the only force on those tires as we are starting is static friction. So looking at a problem like this, mu sub s times the normal force is equal to mg. So mu sub s times m times g is equal to mass times acceleration. So you get rid of that, you get rid of that. We know that, so we can solve for the coefficient of friction. So in this case, mu sub s is equal to a over g. So that is equal to 12. I'm going to leave out the units. Well, no, I'm not, because I'll show you how they cancel. Meters per second divided by 9.8 meters per second. So meters per second squared. So that's going to cancel. That's going to cancel. So let's go ahead and do this. It's going to be pretty darn close to 1.2. So 12 divided by 9.8. It's 1.22. And again, what I always do is I always say, hey, this is about 10, so I get a good estimation of my answer. And so sometimes, as a matter of fact, if you take some tests, they say, hey, assume that g is 10 meters per second squared. Let's see if I can get this to be a little bit better here. So hopefully you're seeing that you're becoming comfortable with the fact that things might cancel each other out. We already went over question 4, and so I think we should be pretty good on friction. One of the things, another type of a question. Let's say that I have a box, and I say, okay, the box has a mass of 25 kilograms, and you're pulling on that with a force. The force is 100 newtons. And I say the coefficient of friction between the two surfaces, say it's already in motion. So the coefficient of kinetic friction is 0.11. And I say, what is the acceleration of this box? All right, let's unpack this problem. Well, we know that we're going to have, in the opposite direction, a kinetic friction force. All right? So we have to go ahead and now analyze the problem because I want to solve for acceleration. What we know is that the sum of all the forces is equal to mass times acceleration. So let's look at all the forces. This is 100 newtons. Now, what is this? Well, the kinetic friction force is mu sub k times m times g. And m times g is just the normal force. So let's get a value for this. So we're going to have, and I hope it works out right. Maybe I shouldn't make these problems up on the fly. 25 times 9.81 times 0.11. So the force of kinetic friction is 27 newtons. So what are the sum of the forces? Well, I have 100 newtons in that direction and 27 newtons in that direction. So the sum of the forces, that's not a very good sum sign. The sum of the forces is equal to 100 newtons minus 27 newtons, and that's equal to ma, mass times acceleration. So 100 minus 27 is what, 73? 73. So 73 newtons is equal to the mass, 25 kgs, times the acceleration. So solving for acceleration, 73 divided by 25, and that's 2.9. So the acceleration is 2.9 meters per second squared. And that makes sense. This force is greater than that force. This is actually called the net force. So another way to think about it. All right, so that is friction. So I'm going to pause this and get set up to talk about springs. Be right back. Okay, springs. Let's take a look at some problems here. So, before we get to problems, let's take a look at some theory. Okay, let's say I have some sort of a surface that's stationary, and I connect a spring to it. That's a really bad looking spring. Well, I can either pull on that spring, excuse me, to elongate it, or I can push on that spring to compress it. Let's take another look at a different sort of a situation. Maybe I have a vertical surface, and let me see if I can make a better looking spring. I have a spring like that, and I can hang weights from it. Now, this delta x, or we can even call that delta x or delta y, whatever you want. This is just the distance that this is either stretched or compressed from the equilibrium length of that spring. Now, this spring, just if you leave it alone, it has a certain equilibrium length. We could call that length x0. So if it's a 18 centimeter spring, it'd be 0.81 meters. If it's a 5 centimeter spring, 0.05 meters or whatever. Now this K value is the force constant for the spring, and that has a unit of newtons per meter. So every meter you stretch it, you have to put a certain amount of newtons into that, newtons of force. Think about springs for a minute. They're very tiny springs, little springs in your watch, or trying to think of a good example that you might have. I don't know if you've ever seen a Slinky. A Slinky is really a spring. It's an old style toy, and you could just stretch it. I can't. I wish I had a Slinky here. I don't. That's a spring. You have springs in the shock absorbers in your car, but they have a much, much higher force constant than your Slinky does. The higher the force constant, the more force it takes to get the spring to either stretch or compress. So if you have a really big value, you're going to have to put a lot of effort into stretching that spring. And you try that sometime. If you ever get like a big spring from a suspension system in a car, you try pulling on it. You're not going to get it very far. But you get a little tiny one, and you could stretch it out to the point where you're going to ruin it. All right. So let's say I've got a spring, and it has a force constant of 150 newtons per meter. Okay. And let's do a problem where I say, okay, I'm going to hang a weight from my spring. And maybe my weight is 75 grams. Okay. Or let's say it's a heavier weight, 7.5 kilograms. Let's see what happens to our spring. So let's say I hang a 7.5 kg mass from this spring, and I say, how much will the spring stretch? In other words, solving for delta x. Let's see if this problem makes sense, because I'm making it up as I go along, but the theory is the same. All right, what's the force? Well, the force is m times g. So m times g, 7.5 times 9.81. So this is going to give me a value of 73.6 newtons. All right. So how far will it stretch? Well, you have to kind of look at this negative sign and interpret it. All I'm asking you for is the change in position. So that negative sign represents the fact that this spring wants to pull in opposition to your stretching. So I hate to say we can disregard it, but if we just want to get a value for delta x, the magnitude of the value, we can disregard it. So let's see what we've got here. We've got a force, and our force is 73.6 newtons. So 73.6 newtons is going to be equal to our k value, 73.6 times delta x. Oh, that should be, no, hang on, that's wrong, that's wrong. I need the force constant there. Give me a little break, I'm getting distracted. So our force, 73.6 newtons, is equal to 150 newtons per meter times delta x. Sorry about that mistake. So let's go ahead and we'll divide through. So 73.6 newtons divided by 150 newtons per meter. That's going to be roughly about half a meter. Remember, the newtons cancel, your meters will come upstairs. So 73.6 divided by 150, and it's going to stretch by 0.49 meters. Pretty easy stuff. So that's the type of a question I could ask. I could also say, hey, how much force would it take to stretch a spring by 10 centimeters if you have a given force constant? That's pretty easy too. And again, take this negative sign and try to interpret what it means. It just means that the spring is pulling back, but you have to apply that amount of force. So that negative sign on your end goes away. On the spring's end, it wants to pull back. All right, so I hope that's pretty straightforward. I'm going to stop this video, come back with part 3 on circular motion.